Cryptography is the practice and study of techniques for secure communication in the presence of adversarial behavior. To properly understand cryptography, it is essential to understand the mathematics of cryptography. This video is intended to help the audience better understand the mathematics of cryptography by highlighting the following objectives: to review integer arithmetic, concentrating on divisibility and finding the greatest common divisor using the Euclidean algorithm, to understand how the extended Euclidean algorithm can be used to solve linear Diophantine equations, to solve linear congruent equations, and to find the multiplicative inverses, to emphasize the importance of modular arithmetic and the modulo operator, because they are extensively used in cryptography, to emphasize and review matrices and operations on residue matrices that are extensively used in cryptography, to solve a set of congruent equations using residue matrices. In this video we will be covering integer arithmetic, modular arithmetic, matrices and linear congruence. In integer arithmetic, we use a set and a few operations. You are familiar with this set and the corresponding operations, but they are reviewed here to create a background for modular arithmetic. The set of integers, denoted by z, contains all integral numbers, with no fraction, from negative infinity to positive infinity. In cryptography, we are interested in three binary operations applied to the set of integers. A binary operation takes two inputs and creates one output. Three common binary operations defined for integers are addition, subtraction, and multiplication. Each of these operations takes two inputs, A and B, and creates one output. The two inputs come from the set of integers. The output goes into the set of integers. Note that division does not fit in this category because, as we will see shortly, it produces two outputs instead of one. In integer arithmetic, if we divide A by n, we can get Q and R. The relationship between these four integers can be shown as A equals Q times n plus R. In this relation, A is called the dividend, Q, the quotient, n, the divisor, and R, the remainder. Note that this is not an operation, because the result of dividing A by n is two integers, Q and R. We can call it division relation. Divisibility is a topic often encountered in cryptography. If A is not 0 and we let R equal 0 in the division relation, we get A equals Q times n. We then say that n divides A, or n is a divisor of A. We can also say that A is divisible by n. We are not interested in the value of Q. If the remainder is 0, we write it as A divides n. If the remainder is not 0, then A does not divide n. The following are several properties of divisibility. Property 1. If A divides 1, then A equals plus or minus 1. Property 2. If A divides B and B divides A, then A equals plus or minus B. Property 3. If A divides B and B divides C, then A divides C. Property 4. If A divides B and A divides C, then A divides M times B plus N times C, where M and N are arbitrary integers. A positive integer can have more than one divisor. For example, the integer 32 has 6 divisors: 1, 2, 4, 8, 16, and 32. We can mention two interesting facts about divisors of positive integers. Fact 1. The integer 1 has only one divisor, itself. Fact 2. Any positive integer has at least two divisors, one and itself, but it can have more. Greatest common divisor. One integer often needed in cryptography is the greatest common divisor of two positive integers. Two positive integers may have many common divisors, but only one greatest common divisor. For example, the common divisors of 12 and 140 are 1, 2, and 4. However, the greatest common divisor is 4. The greatest common divisor of two positive integers is the largest integer that can divide both integers. Euclidean algorithm, finding the greatest common divisor, GCD, of two positive integers by listing all common divisors is not practical when the two integers are large. Fortunately, more than 2,000 years ago a mathematician named Euclid developed an algorithm that can find the greatest common divisor of two positive integers. The Euclidean algorithm uses two variables, R1 and R2, to hold the changing values during the process of reduction. They are initialized to A and B. In each step, we calculate the remainder of R1 divided by R2 and store the result in the variable R. We then replace R1 by R2 and R2 by R. The steps are continued until R2 becomes 0. At this moment, we stop. The GCD, A, B, is R1. Note, when GCD, A, B, equals 1, we say that A and B are relatively prime. Euclidean algorithm example. Find the greatest common divisor of 25 and 60. We chose this particular example to show that it does not matter if the first number is smaller than the second number. We immediately get our correct ordering. Solution. We have GCD 25, 60 equals 5. The extended Euclidean algorithm. Given two integers a and b, we often need to find other two integers, s and t, such that sxa plus txb equals GCD, a, b. The extended Euclidean algorithm can calculate the GCD, a, b, and at the same time calculate the value of s and t. The extended Euclidean algorithm uses the same number of steps as the Euclidean algorithm. However, in each step, we use 3 sets of calculations and exchanges instead of 1. The algorithm uses 3 sets of variables, r's, s's, and t's. Extended Euclidean algorithm example. Given a equals 161 and b equals 28, find GCD, a, b, and the values of s and t. Solution. R equals R1 minus Q times R2, S equals S1 minus Q times S2, T equals T1 minus Q times T2. We use a table to follow the algorithm. We get GCD 161, 28 equals 7, S equals -1 and T equals 6. The answers can be tested because we have -1, x 161 plus 6x 28 equals 7. Linear Diophantine equations. Although we will see a very important application of the extended Euclidean algorithm in the next section, one immediate application is to find the solutions to the linear Diophantine equations of two variables. An equation of type A times x plus b times y equals c. We need to find integer values for x and y that satisfy the equation. Let D equal the greatest common divisor of A and B. If D does not divide C, then the equation has no solution. If D does divide C, then we have an infinite number of solutions. This type of equation has either no solution or an infinite number of solutions. One is called particular. To find the particular solution, use this formula. After finding the particular solution, the general solutions can be found using this formula. A particular and general solutions example. Find the particular and general solutions to the equation 21x plus 14y equals 35. Solution. We have d equals GCD, 21, and 14 equals 7. Since 7 divides 35, the equation has an infinite number of solutions. We can divide both sides by 7 to find the equation 3x plus 2y equals 5. Using the extended Euclidean algorithm, we find s and t's such as 3s plus 2t equals 1. We have s equals 1 and t equals -1. Therefore, the solutions are 5, -5, 7, -8, 9, -11. We can easily test that each of these solutions satisfies the original equation.
Modular arithmetic consists of the modular operator, the set of residues, congruence, operations in Zn, inverses, addition and multiplication tables, different sets for addition and multiplication, and two more sets.
The division relationship, A equals Q times N plus R, discussed previously, has two inputs, A and N, and two outputs, Q and R. In modular arithmetic, we are interested in only one of the outputs. The remainder R. We don't care about the quotient Q. In other words, we want to know what is the value of R when we divide A by N. This implies that we can change the above relation into a binary operator with two inputs A and N and one output R.
As previously mentioned, we can change the division relation into a binary operator with two inputs A and N and one output R. The binary operator is called the modulo operator and is shown as mod. The second input, N, is called the modulus. The output, R, is called the residue. The modulo operator, mod, takes an integer, A, from the set Z and a positive modulus, N. The operator creates a non-negative residue, R. We can say A mod N equals, R. Find the result of the following operations, A. 27 mod 5, B. 36 mod 12, C. -18 mod 14, and D. -7 mod 10. Solution. We are looking for the residue R. We can divide the A by N and find Q and R. We can then disregard Q and keep R. A. Dividing 27 by 5 results in R equals 2. This means that 27 mod 5 equals 2. B. Dividing 36 by 12 results in R equals 0. This means that 36 mod 12 equals 0. C. Dividing -18 by 14 results in R equals -4. However, we need to add the modulus, 14, to make it non-negative. We have R equals -4 plus 14 equals 10. This means that -18 mod 14 equals 10. D. Dividing -7 by 10 results in R equals -7. After adding the modulus to -7, we have R equals 3. This means that -7 mod 10 equals 3. The result of the modulo operation with modulus n is always an integer between 0 and n-1. In other words, the result of a mod n is always a non-negative integer less than n. We can say that the modulo operation creates a set, which in modular arithmetic is referred to as the set of least residues modulo n, or Zn. However, we need to remember that although we have only one set of integers, z, we have infinite instances of the set of residues, Zn, one for each value of n. Congruence. In cryptography, we often use the concept of congruence instead of equality. Mapping from Z to Zn is not one-to-one. Infinite members of Z can map to one member of Zn. For example, the result of 2 mod 10 equals 2, 12 mod 10 equals 2, 22 mod 2 equals 2, and so on. In modular arithmetic, integers like 2, 12, and 22 are called congruent mod 10. To show that two integers are congruent, we use the congruence operator. We add the phrase, mod n, to the right side of the congruence to define the value of modulus that makes the relationship valid. The congruence operator looks like the equality operator, but there are differences. First, an equality operator maps a member of Z to itself. The congruence operator maps a member from Z to a member of Zn. Second, the equality operator is one-to-one. The congruence operator is many-to-one. The phrase, mod n, that we insert at the right-hand side of the congruence operator is just an indication of the destination set, Zn. We need to add this phrase to show what modulus is used in the mapping. The symbol mod used here does not have the same meaning as the binary operator. In other words, the symbol mod in 12 mod 10 is an operator. The phrase, mod 10, in 2 congruent to 12, mod 10, means that the destination set is Z10. A residue class, A, or, A, n is the set of integers congruent modulo n. In other words, it is the set of all integers such that x equals A, mod n. For example, if n equals 5, we have 5 sets, 0, 1, 2, 3, and 4. The integers in the set, 0, are all reduced to 0 when we apply the modulo 5 operation on them. The integers in the set, 1, are all reduced to 1 when we apply the modulo 5 operation, and so on. In each set, there is one element called the least, non-negative, residue. In the set, 0, this element is 0, in the set, 1, this element is 1, and so on. The set of all of these least residues is what we have shown as Z5 equals 0, 1, 2, 3, 4. In other words, the set Zn is the set of all least residue modulo n. Operations in Zn. The three binary operations, addition, subtraction, and multiplication, that we discussed for the set Z can also be defined for the set Zn. The result may need to be mapped to Zn using the mod operator. Actually, two sets of operators are used here. The first set is one of the binary operators, plus, minus, and times. The second is the mod operator. We need to use parentheses to emphasize the order of operations. The inputs, A and B, can be members of Zn or Z. Example. Perform the following operations. The inputs come from either Z or Zn. A. Add 17 to 27 in Z14. B. Subtract 43 from 12 in Z13. C. Multiply 123 by -10 in Z19. Solution. The following shows the two steps involved in each case. 17 plus 27, mod 14. 44, mod 14 equals 2. 12 minus 43, mod 13. -31, mod 13 equals 8. 123 times, -10. Mod 19, -1230, mod 19 equals 5. Properties. We mentioned that the two inputs to the three binary operations in the modular arithmetic can come from Z or Zn. These three properties allow us to first map the two inputs to Zn, if they are coming from Z, before applying the three binary operations, plus, minus, and times. This is the process before applying the properties, and this is after. As you can see, the process is longer when we apply the properties. We should remember that in cryptography we are dealing with very large integers. Applying the properties make the first two operands smaller before the multiplication operation is applied. Inverses. When we are working in modular arithmetic, we often need to find the inverse of a number relative to an operation. We are normally looking for an additive inverse, relative to an addition operation, or a multiplicative inverse, relative to a multiplication operation. Additive inverse. In Zn, two numbers a and b are additive inverses of each other if a plus b is congruent to 0, mod n. In Zn, the additive inverse of a can be calculated as b equals n minus a. For example, the additive inverse of 4 in Z10 is 10 minus 4 equals 6. In modular arithmetic, each integer has an additive inverse. The sum of an integer and its additive inverse is congruent to 0 modulo n. Note that in modular arithmetic, each number has an additive inverse and the inverse is unique. Each number has one and only one additive inverse. However, the inverse of the number may be the number itself. Example, find all additive inverse pairs in Z10. Solution. The 6 pairs of additive inverses are 0, 0, 1, 9, 2, 8, 3, 7, 4, 6, and 5, 5. In this list, 0 is the additive inverse of itself, so is 5. Note that the additive inverses are reciprocal. If 4 is the additive inverse of 6, then 6 is also the additive inverse of 4. In cryptography we often work with inverses. If the sender uses an integer as the encryption key, the receiver uses the inverse of that integer as the decryption key. If the operation, encryption/decryption algorithm, is addition, Zn can be used as the set of possible keys because each integer in the set has an additive inverse. On the other hand, if the operation, encryption/decryption algorithm, is multiplication, Zn cannot be the set of possible keys because only some members of the set have a multiplicative inverse. Each member of Zn has an additive inverse, but only some members have a multiplicative inverse. Each member of Zn asterisk has a multiplicative inverse, but only some members have an additive inverse. Cryptography often uses two more sets, Zp and Zp asterisk. The modulus in these two sets is a prime number, with only two divisors, integer 1 and itself. The set Zp is the same as Zn except that n is a prime. Zp contains all integers from 0 to p-1. Each member in Zp has an additive inverse, each member except 0 has a multiplicative inverse. The set Zp asterisk is the same as Zn asterisk except that n is a prime. Zp asterisk contains all integers from 1 to p-1. Each member in Zp asterisk has an additive and a multiplicative inverse. Zp asterisk is a very good candidate when we need a set that supports both additive and multiplicative inverse. A matrix is a rectangular array of L times m elements, in which L is the number of rows and m is the number of columns. If a matrix has only one row, L equals 1. It is called a row matrix. If it has only one column, m equals 1. It is called a column matrix. In a square matrix, in which there is the same number of rows and columns, L equals m. Operations and relations. In linear algebra, one relation, equality, and four operations, addition, subtraction, multiplication, and scalar multiplication, are defined for matrices. Two matrices can be added if they have the same number of columns and rows. This addition is shown as C equals A plus B. Subtraction is the same except that each element of B is subtracted from the corresponding element of A. Example, multiplication of matrices. The result of the product of a row matrix, 1 times 3, by a column matrix, 3 times 1, is a matrix of size 1 times 1. Multiplication of a row matrix A by a column matrix B is equal to matrix C. Cryptography often involves solving an equation or a set of equations of one or more variables with coefficient in Zn. This section shows how to solve equations when the power of each variable is 1, linear equation. To solve equations involving a single variable of the form A times x congruent to B, mod n. An equation of this type might have no solution or a limited number of solutions. Assume that the GCD of A and n equals D. If D does not divide B, there is no solution. If D divides B, there are D solutions. If D divides B, we use the following strategy to find the solutions. 1. Reduce the equation by dividing both sides of the equation, including the modulus, by D. 2. Multiply both sides of the reduced equation by the multiplicative inverse of A to find the particular solution x0. 3. The general solutions are x equals x sub 0 plus k times D divided by n, 4k equals 0, 1, 2, d minus 1. Example 1, solve the equation 10x congruent to 2, mod 15. Solution, first we find the GCD, 10 and 15, equals 5. Since 5 does not divide 2, we have no solution. Example 2, solve the equation 14x congruent to 12, mod 18. Solution, note that GCD, 14 and 18, equals 2. Since 2 divides 12, we have exactly two solutions, but first we reduce the equation. Both solutions, 6 and 15, satisfy the congruence relation, because 14 times 6, mod 18 equals 12, and also 14 times 15, mod 18 equals 12. We can also solve a set of linear equations with the same modulus if the matrix formed from the coefficients of the variables is invertible. We make three matrices. The first is the square matrix made from the coefficients of variables. The second is a column matrix made from the variables. The third is a column matrix made from the values at the right-hand side of the congruence operator. We can interpret the set of equations as matrix multiplication. If both sides of congruence are multiplied by the multiplicative inverse of the first matrix, the result is the variable matrix at the right-hand side, which means the problem can be solved by a matrix multiplication. Solve the set of following three equations: 3x plus 5y plus 7z congruent to 3, mod 16, x plus 4y plus 13z congruent to 5, mod 16, 2x plus 7y plus 3z congruent to 4, mod 16. Solution, here x, y, and z play the roles of x1, x2, and x3. The matrix formed by the set of equations is invertible. We find the multiplicative inverse of the matrix and multiply it by the column matrix formed from 3, 5, and 4. The result is x congruent to 15, mod 16, y congruent to 4, mod 16, and z congruent to 14, mod 16. We can check the answer by inserting these values into the equations.